Hello, Physics 2. Finally, some new material. We're going to start chapter 36. This is on magnetism. Physics 2 is about electromagnetism, and we're just now finally getting to the magnetism part of that. I've said it before, magnetism and electricity, they're like opposite sides of the same coin. They're not the same thing, but they're very, very much related. So let's get started with that. So, chapter 36, magnetism. So, people have known about magnets and magnetism for a very long time, for millennia actually. They noticed a long time ago that there are these certain rocks called lodestones, naturally magnetized pieces of the mineral magnetite that would attract iron. So in this map, we're looking at what was then called Anatolia. Now it is called Turkey, and this is Magnesia in Turkey. So this is a Greek colony. So Greece, if this map were bigger, Greece would be over here. So the Greeks had a colony over here, and apparently they had a lot of this magnetite. So that's what they ended up calling this rock, magnetite, after the area it was from, Magnesia. So I don't know all the Greek letters, but mu, alpha, gamma. So mag. This is actually not a V; it's a nu, N, etc., etc. Magnetus lithos, lithos meaning stone. So yeah, knowledge courtesy of Wikipedia, of course. So yeah, we've known about magnets for centuries. It wasn't until the 11th century, so the 1000s, that the Chinese developed a magnetic compass. And a century later, the Europeans did that too. So centuries after that, this guy, William Gilbert, very fancy dresser, he published this book called On the Magnet and Magnetic Bodies, and on that great magnet, the Earth, which correctly held that the Earth itself was magnetic. That great magnet, the Earth. So apparently up to this point, when he published this, a lot of people, they had crazy ideas about why compass needles worked. They'd known how, to use a compass for centuries by this point, but they didn't know what was actually drawing the compass needle to the north. Some people actually thought it was Polaris, the North Star itself, that was somehow drawing the compass needles. And other people thought, well, we know that there are lodestones and they can attract, iron, and they can attract the magnetic needle. So maybe at the North Pole, there's a big island made out of a giant chunk of lodestone. So those ideas were incorrect. But it took William Gilbert to publish this to finally kind of set the record straight. So Gilbert's ideas, by the way, also influenced Johannes Kepler's ideas on orbits. So another guy working as a contemporary of this guy in a very different field, but if you're taking astronomy, you might find that interesting. Yeah, Kepler read this book and it influenced his ideas. So a few hundred years later, in 1820, this guy on the left, Hans Christian Ørsted, which you spell this way, but apparently over there you would spell this way, discovered that a current moving through a wire created a magnetic field. He discovered this quite by accident. He just happened to connect a wire up to a battery or a voltaic pile, they would have called it at the time, and noticed that a very nearby compass, the needle of that compass actually deflected when he connected the wire to the battery. So yeah, a current, which is moving charge, causes a magnetic field. Now, important idea. Stationary charges do not create magnetic fields. If you take a proton or an electron and you just put it on the table, it won't make a magnetic field for you. It has to be moving. If it's moving, it will. So kind of the flip of this. A little while later, Michael Faraday, we've seen him before, he discovered that a changing magnetic field near a loop of wire causes a current. So moving charge causes a magnetic field. A changing magnetic field near a loop of wire can cause a current. So a changing magnetic field can cause charge to move. So constant magnetic fields do not cause currents, but changing magnetic fields do. This, by the way, is exactly how an electric guitar pickup works. Maybe we'll get to that later in the chapter. I haven't made that slide yet if we do. So yeah, Ørsted, Faraday, and then this guy, James Clerk Maxwell, he brought it all together. So these are Maxwell's equations in calculus form, in integral and differential form. So in physics, everyone knows Newton and everyone knows Einstein, but if there was going to be a third guy, it would actually be this guy, James Clerk Maxwell. Scottish physicist, fairly short-lived, apparently. And yeah, he took all of the work that was going on in electricity and magnetism at the time and put it together in a gigantic theory and kind of unified the whole thing. You would say that, yeah, Maxwell unified electricity and magnetism. So that's huge. And if you see this picture down here, at least if you're taking astronomy, these are changing electric and magnetic fields. E for electric field, B for magnetic field. We'll get to that soon. That's what light actually is. And Maxwell's the guy who discovered this. So again, everyone knows Newton, everyone knows Einstein. You should probably know this third guy too, Maxwell. So some things you've heard about magnets before. Magnets have poles. We call them north and south. We don't call them positive and negative. We call them north and south. And if you have a bar magnet like this or a horseshoe magnet like this, the poles are where the magnetic field is the strongest. So kind of like the way electric fields work, like poles repel and opposite poles attract. Like charges repel, opposite charges attract. Well, like poles repel and opposite charges attract. So if you have a compass, the north pole of your compass needle is attracted to the Earth's north pole because, perhaps somewhat surprisingly, the Earth's north pole is actually magnetically a south pole. If you were to draw the magnetic field of the Earth, it would look like this. And the fact that these lines are going in here and coming out here means that the geographic south pole of the Earth is actually a magnetic north pole. And the geographic north pole of the Earth is actually a magnetic south pole. And neither of the poles lines up on the axis on which the Earth spins. Don't worry about that. But as someone who teaches astronomy, I'm kind of obliged to tell you that. So, although like poles repel and opposite poles attract, magnetic poles are different than electric charges in a very important way. It is relatively easy to separate and isolate electric charges. If you drag your feet across the carpet, you're going to build up static charge. You have separated positive and negative charges. There's lots of ways to do it. Rub a balloon on your hair. You will have separated positive and negative charges. You can't do that with magnetic poles. Magnetic poles cannot be separated. If you take a big bar magnet and you cut it in half, you don't have a north over here and a south over here. You've turned one big magnet into two little magnets. And you can keep cutting it down, and you would keep getting smaller and smaller magnets. So, important idea. There are no magnetic monopoles. Nobel Prize instantly to anyone who discovers one, but you won't do it because there aren't any. There are no magnetic monopoles. Charge you can separate. There are positive charges. There are negative charges. When you're dealing with magnetism, every time you have a north, you also have a south. They're monopoles. They are not monopoles. So think back to chapter 32, electrostatics. What is the symbol and the unit for electric charge? So for some reason, we all got a big laugh out of this. The symbol for charge is Q, and its unit is the Coulomb, C. So what is Coulomb's law? You may not remember that we call it this, but it's this one. So there's Coulomb. The electric force is equal to that constant K, that's Coulomb's constant, times one charge times another charge divided by the distance between the charges. So it looks very similar in form to Newton's law of universal gravitation. And then what is the formula for the electric field from a point charge? So way back then, chapter 32, you might remember this formula. So Faraday, this is a young picture of Faraday. He's the guy that developed the idea of fields, which philosophically was very weird at the time, if you remember from chapter 32. And this is your formula for the electric field from a point charge, Q. Now, we had these equations when we were doing electric fields. You're not going to have analogous equations when you're doing magnetic fields because you don't have magnetic monopoles. There's no such thing as a magnetic charge because you just can't separate them completely the way you can with electric charge. So we draw magnetic field lines. These look kind of similar to electric field lines, and some of the rules are basically the same. So the direction of the magnetic field is tangent to the field lines at any point. So, if you wanted to figure out the field right here, you would draw the tangent and you would say the field's going this way at this point right here where this little arrowhead is. And the number of lines per unit area, or in this case, volume. This is a two-dimensional picture, but it's representing a three-dimensional idea. So yeah, area on the page, but volume in space. Anyhow, the number of lines per unit area or volume is proportional to the strength of the magnetic field. So where you have more lines close together, you have a stronger magnetic field. And again, this is very similar to how we drew electric field lines. So when we drew electric field lines, maybe you can think of this as kind of a stretched out version of these. If these charges were separated a little bit further, it would start to look more like this. But anyhow, electric field lines start on positive charges, so they start here. They end on negative charges, and some of them will go off to infinity. So like this guy will just go off forever in this direction and never come around to this guy. If it starts here and it's near enough to this guy, it will end on that guy. So that is how electric field lines go. Magnetic field lines are different. So watch the animation right here over the magnet. Took me a while. It's hard to animate things in Google Slides. But anyhow, magnetic field lines don't actually start or end anywhere. They don't start at the north and end at the south. If you look carefully, if you could look inside the magnet, you would see the field lines continue right through the magnet. They're always forming loops. And therefore, they don't extend to infinity. So if you see a magnetic field line, even this one here, eventually will curve around one way or another and come back this way. It's got to be a closed loop. So yeah, magnetic north and south, kind of similar to electric positive and negative, but not really. They're different in some important ways. So magnetic fields can get very complicated. Well, electric fields can get very complicated too. So can magnetic fields. So if you have a couple of bar magnets arranged like this, you've got this weird pattern like, seen here. So that looks kind of weird. So this is an image representing the magnetic field of the sun. If you're taking astronomy, you know that the sun's got crazy magnetic fields going on because of all the plasma, is all charged particles moving around, and it's all related. It's all crazy. It causes sunspots and solar flares and coronal mass ejections, all kinds of things. So yeah, at the top of this slide, magnetic fields can get very complicated. Sometimes they can be simple though. You can take the ends of some bar magnets, bring them close together, and in the area between, you have a fairly uniform field, and you could draw the field going to the left, or to the right, or to the up, or to the down. So hopefully that's clear enough. This next idea might be a little bit weird. You can also have magnetic field lines going into the page or coming out of the page. The fact that this is a three-dimensional thing is going to be very important throughout this chapter. So if you're looking here at the left, this is a magnetic field. These are two different ways of representing it. You would do it this way with the circled X's or just the open X's like this. But this is a magnetic field going into the page. So think of an arrow that's flying away from you. And if you look at that arrow, you're seeing the tail feathers. So yeah, an X is a magnetic field going into the page. On the other hand, if the arrow is flying towards you, you're going to see the tip of the arrow. You're going to see the point. So you draw it either has a dot with a circle around it or just the dots. So left, right, up, down, into the page, out of the page. So on April 21st, 1820, hey, that's almost 200 years ago today, if you're reading this week, or the week that I'm recording it. So Danish physicist Hans Christian Ørsted discovered something surprising. Current flowing through a wire caused a nearby compass needle to deflect. So yeah, again, he discovered this completely by accident. It's a huge discovery, though. He just happened to connect a wire to the terminals of a battery when a compass was nearby. And when he did so, he happened to notice it made the compass needle move. So this is really, the first time we knew of the connection between electricity and magnetism. And we actually know the date. So you would call this Ørsted's law, that electric currents create magnetic fields. So the symbol for magnetic field is a B, and it should have a hat on it, but I can't draw the hat in Google Slides. And when you have a current flowing, it wraps around the currents in a particular direction according to a right-hand rule. We're going to have a couple different right-hand rules in this chapter. So here is the first right-hand rule. We'll call this Ampere's right-hand grip rule, or just the grip rule, or just Ampere's rule, something like that. But yeah, the first right-hand rule. If you were to grab a wire and you held your thumb, you just grab it with your fist, and you held your thumb in the direction that conventional current, meaning that the positive charge was flowing, the magnetic field created by that current would wrap around the wire in the same direction that your fingers wrap around your fist. So this is the grip rule. So point your thumb in the direction of the current and your fingers wrap around in the direction of the magnetic field. So I've heard this right hand rule and the other one taught differently. I'm always going to try to keep it a certain way. The way I teach it, your thumb is always the direction of current or the direction of positive moving charge, and your fingers are always the magnetic field. So yeah, here's the grip rule. So look at this picture here. So you've got current flowing in down along this wire, does this loop like this. Oh, sorry, my mouse ran into something. Does this loop like this, comes along here. So determine the direction of the magnetic field right here in the middle of the wire. So hold your right hand in front of your face and trace out with your thumb the path of that and try to figure out what is the direction of the magnetic field, like right here. If you do it correctly, you'll get this. So yeah, it's messy. It's going all over the place, but right here inside the loop, it's going, this is a three-dimensional picture. It's going kind of left to right. So yeah, that's the right-hand rule. So another example of the right-hand rule. So imagine, you're looking at, well, you don't have to imagine, you're looking at your screen. On your screen, there's a loop of wire, and current is going through the wire this way. Never mind the fact that I don't have any battery or anything to motivate this current. But yeah, current's going through the wire this way. Use the right-hand rule and determine the direction of the magnetic field inside the loop and outside the loop. So what you should do is hold your hand in front of the face, match it to an arrow, see which way your fingers are going, and try to determine which way your magnetic field is going to go inside the loop and outside the loop, and think, how would you represent that magnetic field? Well, inside the loop, the magnetic field is going to point into the page. So we get the X's. We're looking at the tail feathers. Outside the loop, the magnetic field would point out of the page. So outside the loop, the current would be coming towards you. So it's moving out of the page. And it wouldn't be nearly this even, but I made this using, basically text graphics in Google Drawings. So what can you do? But yeah, the right-hand rule. You'll spend a large part of this chapter when you're doing these problems holding your right hand in front of your face and pointing it in different ways and trying to bend your wrist and your forearm to represent the direction of currents and magnetic fields. You will look silly, just get used to it. So, same picture. Now, think of this as just kind of a clock on the wall, and imagine the area of space in a plane that is right above this. And by above, I mean it's a little bit closer to you than this circle itself. So if you were to reach out and touch the screen right here at 12 o'clock, well, now pull your finger back a little bit and figure out which way is the magnetic field going at that point that's right above the 12 o'clock. And then also use the right-hand rule and figure out what's the magnetic field doing at a point at 3 o'clock. So at 12 o'clock, the magnetic field is going to point down. If you're over there at 3 o'clock, the magnetic field is going to point to the left. So yeah, right-hand rule, Ampere's right-hand grip rule. So, quick review. Who discovered that a current moving through a wire created a magnetic field? That would be Hans Christian Ørsted in 1820. Who discovered that a changing magnetic field near a loop of wire caused a current? That would be our old friend Michael Faraday. So we'll get to that idea later in the chapter. And who was it that took Ørsted's idea and Faraday's idea and Ampere's idea and this Biot and Savart and a whole bunch of other ideas and put them all together and kind of unified all of electromagnetism? This, relatively unknown in the popular imagination anyway, but real total giant of physics, one of the big three, James Clerk Maxwell. So what would happen if you cut a bar magnet in half? Do you end up with a north piece and a south piece? No, of course you don't. You end up with two smaller bar magnets. Each one has a north and a south. This is because there is no magnetic monopole. You can't separate the poles of a magnet the same way you can separate positive and negative charge. So how would you represent a magnetic field going into the page or out of the page? Well, if it's going into the page, you would be watching the tail feathers of the arrows fly away from you. So you would see the X's that are, the tail feathers, also called fletching. Someone who makes, the tail feathers of arrows, they're called a fletcher. So that's where that word and that last name comes from. Yeah, trivia. And same token, if the arrow is coming towards you, if the magnetic field is coming out of the page, if it's coming towards you, you would see the points of the arrows. I don't know if there's a particular name for the person who makes the tips of the arrows, but the person who puts the whole arrow together is called an arrowsmith. So what is the symbol for magnetic field? It is, of course, B with a hat. Yeah, I don't know why it's B, but it's B with a hat. Totally a vector. This stuff is vector as anything. So in Ampere's right-hand grip rule, what does your thumb represent and what do your fingers represent? Well, your thumb represents the direction of the positive current, also called the conventional current. So if the current is flowing up through the wire, the magnetic field would be wrapping around like this. So in this drawing, we're kind of looking down on it a little bit, and the way we're looking at it, we would say it's going counterclockwise that way. So there is your first right-hand rule. And that's it for this part of the slides. Hopefully you found that helpful.